مرحبا طلاب. I told you in the last video that if we run this program 5.1, we get 4 responses because we have 2 input, 2 output. 2 output due to input 1 and 2 output due to input 2. This is, you can see on page 177 if you want to read in the book or follow it up in the book. Program 5.2, which is on page 177 also, will show you 2 output, y1 and y2 due to u1 separately. They are plotted on above and on top. They are plotted on top, and y1 and y2 due to u2, working on superposition theorem. That means when he find the output due to u1, he'll put u2 equal to 0. That's how the program works. And you'll see the plot on page 178. Okay. Now, state space modeling. This is section 5.3 model when no input of derivative. You know the last example we considered, the spring mass and damper, and the force was into the mass. So if we have the spring into the mass, this means that you have only the input, we don't have a derivative. Like you have a transfer function like 10 over كذا on the denominator. But if we have, this is the case when we have the force is going directly into the mass. Now I will show you this is this if we have an input, if we have a force, it's going through other element, not the mass, especially due to a damper. I will show you this idea through an example. Also, this example will represent you a higher order system, so we can have an A matrix more than 2 by 2, like 4 by 4 or etc. Okay. Excuse me. The example is here in front of you. I have 2 masses. I have 2 points to take as distances. And I have this spring 1, spring 2, and damper. And we have the force is going into the mass. It's similar to that example which we have before, but here we have a higher order system. And we have the data in here. You can read it or you can have a look at it in the book. We need to find response plots. Z1, I need to have the response. This is the motion of the system for Z1, Z2, and the difference between them. Okay, so I'll have the responses Z1, Z2, and Z1 minus Z2 first time. Of course, you can write the equation easily, I suppose. Is M1 Z1 double dot equal to minus K1 Z1 minus K2 Z1 minus Z2, and minus B times Z1 dot minus Z2 Z2. This is Z2 dot. And the other equation, M2 Z2 double dot equal minus K2 Z2 minus Z1 minus B Z2 dot not minus Z1 dot plus F. So if we have the states, because we have 2 motions, we have x1 equal x1, x2 equal z1 dot, x3 equal z2, and x4 equal z2 dot. So we have 4 states, okay? 4 states. This means that, sorry, this means that A matrix will be 4 by 4. Now arrange the equation as you know, and put the highest derivative into the left-hand side of the equation. So we have x1, x2 dot. So I have x2 dot here, x2 dot equal to this, x1 minus b over m1 x2 plus k2 over m1 x3 plus b plus m1 over x4. Now this in here, I don't have a force because the force is on the other mass. And this is the other equation, x4 dot equal k2 over m2 x1 plus b over m2 x2 minus k2 over m2 x3 minus b over m2 x4 plus 1 over m2 alpha times u. Alpha is a factor so that you can choose your u, of course, is a unit step. So the force, you can make it of a level, you can change it into MATLAB. So here he chosen alpha equal to 10, so that means you have a step of 10. Okay, so also we have x1 dot equal x2. Now we can write the equation, the total equation. We have sorry, I'll start again. This x2 dot, one equation. This is x4 dot, another equation. And we had at the beginning, we assumed that x1 equal to z1 for x1 dot equal x2, x3 dot equal x4. So put there in here, this is x1 dot, x1 equal x2, so 0, 1, 0, 0. And x3 dot, we have x2 dot, which is that equation. We put it in the matrix. This is for x2 dot. This is for x3 dot equal x4, that one. Okay, and this one is from x4 dot, this one, and equal to, you notice that only the fourth equation, x4 dot, equal to have an input force. So we have the B matrix 0, 0, 0, alpha over m2. You notice that we have two mass, like 2 degrees of freedom, let's consider it. So we have A equal 4, 1, 2, 3, 4 by 4, 1, 2, 3, 4, and B equal 4 by 1, single input, let's say. Output equation Z1 equal X1, which equal Y1, Z2 equal X3 equal Y2. So if we have Y1, Y2, Y1 equal to X1, that means 0. Don't know if it's clear. Y1 equal X1, and Y2 equal X3, that's one. And we don't have a D, because we don't have any connection between the input, the force, and the output, right? These are the model. So you have now, once you have the A, the B, and C, and D, you can put them into the MATLAB, and you can see the equation. Now, if we substitute the value he's given, numerical values given to us in the example, we can see that A will be 0, 1, 0, 0, minus 9, minus 2, 6, 2, 0, 0, 0, 1, 3, 1, minus 3, minus 2. Sorry, they are a bit near to each other, together. And B equals 0, 0, 0, 0.5, alpha 10, and M2 is 20, it's 0.5. And this is C, which is doesn't need any data. Only the A need the data which are given to you. MATLAB program, which is given to you, which is program number 5.5, produces the responses Z of t, Z1 of t, Z2 of t, and Z1 minus Z2 versus time. Okay? I would like to study this program. You don't have to do anything. Just punch it into your laptop in MATLAB, put this program on a MATLAB, and get the responses here. Sorry, get the responses as shown in figure 12. This is the program which I need you to just put it into your MATLAB and see, do you get the same responses? If you didn't get this, and that will give you a practice. The other thing, I have to give you some homework so that I can put you some marks on it and apply it and get the responses. The responses will be here. So this is Z1. That means this means that the distance, if you consider it as the output, we have displacement or distance. So it is actually very oscillatory. So it will be oscillating, but damped oscillating. And at the end, it will reach at a value which is less than 0.4, 0.3. And if you see output 2, we'll see that it's 0.5. It's like the steady state of the step, okay? And if the difference between them Z1 and Z2, if you subtract Z2 from Z1, let's say at steady state, which is clear. So if you subtract this one from this one is 0.5. So it's 0.3 minus, it's like a 0.3 or yeah, like 0.3. This one is like 0.3 and this one is 0.5. So that will be a negative for Z1 minus Z2 at steady state. Okay. So try this program and see what are the responses and send me your results, please. Okay, this is done. Now, in section 5.4, we have an input to a system through the elements that give a derivative of the input. Well, how is that? It's when we have the input going through a damper, let's say in this example. So in this example, we have the input going into the damper. So if we write the equation for this system, we'll see that my double dot, I'll go quickly through this because you know this example is simple for you, I'm sure. But here we consider this situation when we have the input coming into, not the mass, coming into another element like the damper that's going to give the derivative of the input. So we'll have like y double dot equal minus k over m y minus b over m y dot plus b over m u dot. So if we try to x1 equal y, x2 equal y dot, so we'll have this state equation, right? Now what do you notice here? We have equation that's containing, before we didn't have any, in any of the state equation we been dealing with, that it have a derivative here. This will create a problem. Not a difficult problem, but it's a lengthy procedure to get the state variable model, I mean the A, the B, and the C, okay? This is the problem. So the book gives you two methods. Both the two methods are lengthy, so I'll take the second method in the book, then in the middle of that method, I'll divert and go and give you a different procedure that will make it easier for you. Otherwise, it will be very, very lengthy procedure, okay?